Right, so I'm going to talk a little bit different to what Mark's just told us about, but we're still working very much in the same area. So using organic chemistry to make useful molecules, basically. And so I basically want to start off by talking about benzene. So benzene is something that I think many of you will have seen before. It's obviously on TV shows. When anyone's talking about chemistry, you'll see a benzene ring as part of a structure, and it's really ubiquitous in everyday life. And so a benzene ring is what I've shown on the top left here, and every sort of kink in the hexagon there is a carbon atom. And so benzene is made up of 6 carbon atoms and 6 hydrogen atoms. And we can draw that in various ways. I guess the one I've drawn in the middle is where I've drawn in the hydrogens explicitly. Often we don't do that because there's lots of hydrogens in a molecule normally, and they're not particularly interesting. So we often draw the benzene ring more like on the left-hand side. But I think it's interesting to think about what shape the benzene ring is. So as you can see from the molecular diagram shown on the top right, benzene is a flat molecule. All of the carbon atoms and all of the hydrogen atoms are all arranged in the same plane, essentially. And I guess I said before already that benzene is ubiquitous in everyday life. And so just to pick 3 very common things that you probably have in your own homes, paracetamol, aspirin, and TCP all contain one of these benzene rings. And so I guess you're very common in chemistry, but benzene, C6H6, it's not the only way that we can arrange 6 carbon atoms and 6 hydrogen atoms. So if we think about some other ways of arranging those atoms, we can see these 4 suggestions here. Now, this isn't all of the suggestions that we could make for C6H6, it's only 4. But nevertheless, I think it's really important to just think about how different these actually look to benzene itself. So the first example I've given here is called duobenzene. Still 6 carbon atoms and 6 hydrogen atoms, but you can see that they're arranged very differently in space. So here we have essentially a bent molecule, no longer a flat molecule. Whereas if we think about fulvene, which is the next molecule I've given, also C6H6, but fulvene, rather like benzene, is flat. And so this is a consequence of the arrangement of the bonds in the molecules. This is what dictates the shape of a molecule. So we can see in the molecules at the top that we have sort of single lines, and then occasionally we have some double lines. So the single lines mean that there's a single bond, and the double lines mean that it's a double bond between 2 carbon atoms. So duobenzene, not flat. Fulvene is flat. If we take on to the next example, it's benzvaline. Again, this is another example of a non-flat molecule. So in other words, a 3-dimensional molecule. Again, we've still got 6 carbon atoms and 6 hydrogen atoms. They're just arranged in a rather different way. And the last example is quite an interesting one. You can probably see even from the way it's drawn at the top that that's not a flat molecule. So this is more Toblerone shaped, for want of a better description. And so we can see again, we have this very 3-dimensional molecule where the carbon atoms are arranged in this very sort of odd shape in a way. And so I guess of these 4 molecules that I've just talked about, none of those are natural molecules. But we can actually make all of them using chemistry. They're quite hard to make, so it's not necessarily a simple synthesis. Prismane, for example, was made in the 70s for the first time. But it's interesting to think about these different shapes and what that might mean in terms of the use of these particular types of molecules. So if we think about making molecules, when we're thinking about making things that contain benzene rings, this is quite easy to do in terms of a synthesis. So benzene itself is available from crude oil. We can get large quantities of benzene. Benzene itself is actually quite toxic, but setting that aside for a minute, if we want to sort of change benzene, so add groups to benzene, this is quite a simple process. So this is many of these sorts of processes are known in the 1800s even, and you start to learn about that sort of chemistry normally at A level, and then you develop that throughout an undergraduate degree, for example. But essentially, it's quite easy to take benzene and to add extra groups of atoms around that benzene ring. So the blue dot here just represents a group of atoms that are non-specified. And those could be carbon and hydrogen atoms, but they could also be other atoms as well. So nitrogen atoms, oxygen atoms, things like that. And so it's actually these atoms in the variable groups that are normally the more active parts of a molecule. So we can add these groups on using various different methods, but I think the key point is that making these benzene-containing molecules is very easy. The benzene rings, as we noted before, are flat. And so when it comes to thinking about how molecules interact with the body or in biological targets, often when we're thinking about developing drugs, we're going to be thinking about interactions with proteins and enzymes, which are normally three-dimensional entities in themselves. So I've given an example of a generic enzyme here on the left-hand side. You can see that it's got various sheets and ribbons, and those represent loads of different atoms arranged in a variety of different ways. But I think the key point is that it's a three-dimensional structure. And there's sort of some evidence to show that three-dimensional small molecules might be able to interact better with things like enzymes, which are also three-dimensional, than the flat molecules that we looked at the start. And I guess a lot of drugs historically have been made from the flat molecules, i.e. the benzene rings, purely because these are easier to make. So when you're thinking about working in pharma and you want to make lots of different molecules to test them, it's quite easy to make a lot of benzene ring type molecules because that chemistry is known and it's very widely used. It's more difficult, though, to make some of the more three-dimensional shapes. So, for example, some of the other isomers of benzene that I mentioned earlier in my talk. And so I guess when we think about how a small molecule might interact with an enzyme, we can use the picture on the right as a general sort of overview of what might be happening. So we have our enzyme. It's three-dimensionally shaped, as we've mentioned. And then you'll have a substrate, i.e. the small molecule that you've designed, which will sort of slot into that enzyme in what we might call an active site, or potentially some other site in an enzyme. And really, when those two things come together, when that small molecule docks into the enzyme, it can change the behavior of the enzyme. And so this is the sort of approach we might take in treating many diseases. Perhaps we need to knock out an enzyme that's having an undesirable effect, or maybe we need to switch on an enzyme that should be doing something, but it's inactive in a certain type of illness, for example. And so there's some evidence to show that 3D small molecules might be, in many cases, better than flat molecules at interacting with these sorts of very complex three-dimensional molecules. So specifically, there's a couple of groups that are quite trendy at the moment in terms of thinking about replacing benzene rings in molecules with these particular types of molecule. So I've given three examples here. We have cubanes, so named because they are cube-shaped. Here, every corner of the cube is a carbon atom. There's also bicyclooctanes, so a different arrangement, again, of 8 carbon atoms. And we also have propylanes on the right-hand side. So again, they're named because they look a bit like a propeller. But all of those you can perhaps see are more three-dimensionally shaped than a benzene ring, which of course is flat. And so the idea is that we try to make more three-dimensional molecules because we might well be able to get better interactions with biological targets that we might be looking to try and target in terms of medicinal chemistry and drug discovery. I guess the focus of most of my, well, half of my group at the moment is on cubanes in particular. And the reason we focused on those is because the size of a cubane, if you look across the top to the bottom, is around the same size as a benzene ring. So a very small difference in sort of the overall length of those two different moieties. What is different, of course, is that cubane is particularly three-dimensionally shaped, whereas a benzene ring is flat. And I guess the other difference we've got here is that cubane has 8 carbon atoms, And each position around the cube, we can accommodate a variable group, so a blue dot in the top example. So that's 8 different groups that we can arrange around a cubane core. And that would be sort of quite spherical in shape if we were to do that because of the 3-dimensionality of the cubane. If we look at the benzene ring, then if we add those groups, variable groups, we have 6 positions this time to add those groups, but they would all be flat, essentially. They'll all be in the plane of the benzene ring. And so this leads to these very flat molecules, which more recently, the pharma companies have started to try and move away from and try and move towards these more 3-dimensional structures. So that's all great. The only problem is that these 3-dimensional molecules are much, much more difficult to make. The chemistry often has not really been very well developed to make these sorts of molecules. And so it's very difficult to get your hands on those molecules, even to test them. And then if you do find that they're very good, we are also short of methods for making them on larger scale. So the approach that my group is taking to this problem is to use photochemistry. So this is chemistry that's driven by light, in particular ultraviolet light in most of the sort of work I do. And photochemistry is very, very underdeveloped. But the advantage of photochemistry is that we can use high energy light to transmit to a starting molecule so that we can make it do chemistry without needing to add things like catalysts or other harsh chemicals to get the reaction to proceed. And so you can think of photochemistry really as taking 2 Lego bricks and sticking them together to form a new compound. So we take a molecule, we shine a light on it in the presence of a second molecule, and we can join those 2 together. So I can give an example here of the red molecule reacting with the blue molecule. In this case, it's the 2 double bonds that are going to react together. So what we do is we take a solution containing the red molecule and the blue molecule, we irradiate it with ultraviolet light, and we just stick those 2 molecules together. So this is sort of the simplicity side of photochemistry, I guess. We just take these 2 things, we don't need to add anything else apart from light, we stick them together, we have our product at the end. And so this also has a role in sustainability as well, which is, of course, what Mark touched on in his talk, in that we don't need to add lots of extra things into the reaction to promote the reaction, because here the UV light is doing that job for us. And so I like to use this quote when I'm talking about photochemistry, because this is back from 1912. So Giacomo Chamichan was one of the forefathers of modern photochemistry in organic chemistry. And you can imagine back in 1912, industry at that time was very much built on lots of smokestacks, pollution was everywhere. And he had this vision that we would use in the future light to do all of these processes. So we wouldn't be burning things anymore, but instead we'd be using light. And that hasn't quite materialized in the way that he sort of was envisaging here, in that photochemistry is still relatively underdeveloped. Nevertheless, there's been a huge drive in photochemistry in recent years, and that's something that my group in particular focuses on. In particular, in the UK, we don't have many groups working with ultraviolet light to do these sorts of reactions. Okay, the other fantastic thing about photochemistry is that because we're using quite high energy light, we can use that light to bend molecules, essentially. So I guess the closest analogy is the Japanese art of origami, where you'd probably be familiar. You take a sheet of paper, you keep folding it successively, and eventually you get to something nice at the end. And so this is basically the approach that my group is taking. If we think about a molecular example of origami, then a good one would be the one we've already looked at earlier in the lecture, where we thought about benzene. If we used ultraviolet light, we do need quite high energy ultraviolet light. So this is more energetic than what you might find in a tanning bed, for example. Then we can make all these isomers of benzene. So these isomers are all less stable than benzene itself, but because we are giving very, very high energy, we can bend this molecule into various different shapes. And so this is a great way to access these sorts of 3-dimensional molecules. And so I'll give you an example of what we're specifically working on at the moment. So there's a few chemical structures there, but don't worry, what we're trying to do is just simplify the approach here. We're thinking about using photochemistry in step 1 to take two things and to stick them together. The product we get of step 1 is a 3-dimensional molecule. We can then do a second step, and this is a non-photochemical step in this case, where we again bend the molecule again and we incorporate a molecule of sulfur dioxide. That gives us another product that we can then do another photochemical reaction in step 3, where we take the two double bonds on the left-hand side and right-hand side of the molecule, and we essentially zip that molecule up to give us a cubane, or almost a cubane. We have one bond left to form in the cubane at that point. And again, we can actually use UV light to essentially rip off the SO2 bit of the molecule again and form our final cubane. And so this is a 4-step synthesis of cubane derivatives, which is much, much more efficient than what is already known in the literature. So if you want to make cubanes at the moment, you'll be looking at 10 to 15 steps to get to those cubane products. Now you'll note that I have dotted arrows for steps 3 and step 4. So this is an ongoing project. We've got through steps 1 and 2, we've optimized those, but it does take quite a lot of work to optimize these sort of chemistry. And so we're still working on step 3 and step 4, but I am confident that we're going to get there soon. So this is, as I say, an ongoing project, but really promising way to make molecules in a sustainable way, and molecules that we can't make using more traditional organic chemistry. Okay, so to bring to a close, I'd like to acknowledge my group who are working on various projects, so graduate students and the project students as well. And I also like to thank those who've given me the money to fund these studies. So in particular, the pharma companies, AstraZeneca and Lilly, who've both sponsored a PhD student each working in my group in this area. Okay, finally, I'd like to thank you for your attention, and do ask any questions if you have them. Thank you.